Okay, so we're talking about expanding the binomials, and yesterday we just looked at it via making use of Pascal's triangle to save doing the whole expansion. I'm going to look at it a little bit more closely. So if I had 1 plus x to some power, let's call it n. So in other words, we're saying 1 plus x times 1 plus x times 1 plus x, and so on and so on and so on, n times. Now when we expand out, what we're essentially doing is taking a term from each of the set of parentheses and multiplying them together. And then we just have to make sure we do every possible one that we can. So for example, I could take x out of the first one, 1 out of the second one, x out of the third one, 1 out of the next 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 one, and so on, and then just take x out of the last one, and I would end up with x cubed. So the question then is, well, how many different ways could I end up with x cubed? Another way of saying that, how many different ways can I choose 3 x's from n sets of parentheses? Well, this is something we dealt with earlier in the year. It's NC3. It's a combination because the order doesn't matter. We just need to make sure we choose 3 x's. So NC3. Therefore, what this means is we don't actually need Pascal's triangle. Because if I want to work out the coefficient of x to the power of k, I know it's going to be NCK. Because I'm going to choose x, I need to give them k times out of the n parentheses. So how many ways can I get k x's out of n sets? Now, when we're dealing with binomials, an alternative way of writing NCK is like this with parentheses. Notice there is no fraction bar there, it's just n over k. So if you see that, that means NCK. So the expansion then for 1 plus x to the power of n would be NC0 plus NC1x, NC2x squared, and so on and so on and so on, up to the last term, which is NCN x to the n. Now, 1 plus x is very limited. If it was a plus b, we could generate a formula for that. The only difference is, like we saw yesterday with our examples, the power of a will start at n and go down by 1 each time. The power of b will start at 0 and go up by 1 each time. At any term we could pick, those two powers will add up to be n. So now if I want to do 2 plus 3x to the power of 4, there it is. Well, it's 4c0 to the power of 4 plus 4c1 2 cubed, power goes down by 1, 3x to the power of 1, it goes up by 1, and so on and so on and so on until I get to the last term. So I don't need to write out Pascal's triangle and read along the row. We can just calculate what 4c0 is, what 4c1 is, and when we put it all together, there's our eventual expansion. So 16 plus 96x and so on. So 3 basic properties of Pascal's triangle then, combining that with combinations. NCK, therefore, must always be n minus 1ck minus 1 plus n minus 1ck. That's the construction of the triangle. If I wanted to work out NCK, so I'd be on the nth row of Pascal's triangle, and I'd go along and I'd say, right, I want to work out the kth one. I would look above in the n minus 1th row, so the one above it, and say, oh, well, I want to get k minus 1 and k, add those two numbers together to get the number I'm looking for. That's how we constructed Pascal's triangle. So that's basically what that property is saying. Let me prove it. So 1 plus x to the power of n, I could rewrite as 1 plus x times 1 plus x to the n minus 1. Now if I expand it out, 1 plus x to the n minus 1, it would be n minus 1c0 plus n minus 1c1x, and so on and so on and so on. Somewhere in the middle, there'd be these two terms, n minus 1c k minus 1, x to the k minus 1, and n minus 1c k, x to the k. Now, I'm interested in x to the power of k. So if I wanted to find x to the power of k, well, on the left-hand side, it's nice and easy, because 1 plus x to the power of n, when we expand it out, we said the coefficient of x to the k will be NCK. Now on the right-hand side, I'd say, well, the 1 I would have to multiply by the x to the power of k term. X I would have to multiply by the x to the k minus 1 term. And so on the right-hand side, the coefficient would be 1 lot of n minus 1 ck minus 1 plus 1 lot of n minus 1 ck. And so there's our proof. I mean, they're both coefficients of x to the power of k, but found two different ways. So therefore, that relationship must be true. Okay, so that's the first pattern. The next one's a little bit easier. NCK will always equal NCn minus k. That's just basically saying it's symmetric. So the n numbers are always the same. Go in once. So the second last number and the second number is always the same. The third last number and the third number is always the same. And so on and so on. So there's symmetry about Pascal's triangle. When you think about it with combinations, if you remember the formula for combinations, that makes sense because something like, let's say 5C2. If I wanted to work out 5C2, I would have said 5 factorial on 2 factorial, 3 factorial. But if I wanted to work out 5C3, I would have said 5 factorial on 3 factorial, 2 factorial. Same thing. So that's the symmetry of Pascal's triangle. And the very last one is simply saying, hey, Pascal's triangle, it always starts and finishes with 1. So NC naught will always equal NCn, and that'll always be 1. So there's the three basic Pascal's triangle relationship. So let's extend this idea a little bit. If we want to expand out some perfect parentheses, well, we know a plus b squared is a squared plus 2ab plus b squared. I mean, we know that. But let's think about it a different way. A plus b squared. Okay. What are all the different ways I could use two pronumerals and come up with, using a and b? So what are all the different terms I could have? Well, I could have a squared, which is a times a. I could have b squared, which is b times b. Or I could have a times b. So there are all the different ways I could use two pronumerals and come up with a term. The question is, what are the coefficients? So how many ways could I arrange two a's? Or two b's. I mean, it doesn't matter which way. And, well, there's only one way of doing that. AA. Well, how many ways could I arrange an A and a B? Well, two ways. I could have A and a B or a B and an A. Or, going back to our permutations idea, 2 factorial. 2 factorial ways of arranging two objects. And so there's our A plus B squared plus 2AB. Essentially the same formula. So extending on that idea then, if I had a plus b plus c plus all the way up to n squared, I could find it by saying, well, if I'm only going to end up with 2 pronumerals, right, which I know I will because I'm squaring it. So I'm going to take 1 pronumeral out of the first one, 1 pronumeral out of the second one. So I'll get 2 pronumerals, multiply them together. I could get a squared, b squared, c squared, and so on. Or I could get a times b, a times c, b times c, b times n, c times n, so on and so on and so on, all those ones. But I'll ask the same questions. Whoops, let me go back. How many ways could I arrange the a and the a? Well, there's one way. How many ways could I arrange the a and the b? There's 2 ways. So there's our formula, if you like, for anything squared. What about cube? Okay, so how can I use 3 pronumerals, but just using a and b? Well, I could have a cubed, I could have b cubed. I've grouped those together. I could have a b squared, or I could have a squared b. And that's pretty much it. So the question then is, how many ways can I arrange those objects? How many ways can I arrange a? Well, there's only one way. How many ways could I arrange an A and 2 B's? So if I was to say to you, how many words could you form using the letters A and 2 B's? Well, that was 3 factorial on 2 factorial. 3 factorial, the number of ways you could arrange the 3 objects. But we got some repeating, so 2 factorial on the bottom. And that creates our formula for the cubic. A cubed plus B cubed plus 3, A squared plus AB squared. Which hopefully we recognise as the cubic. So all right, what about, and we haven't seen this one before, A plus B plus C all cubed. So now I've got 3 pronumerals. I'm going to take 1 out of each. What are all the different things I could have? Well, I could have A cubed, B cubed, C cubed. I could still have the a squared b's, a squared c's, but now there's a few others where I take 2 of one pronumeral and 1 of the other. But now there's this third one. I could take an a out of 1, a b out of 1, and c out of the third one. So I could also have an a, b, c. So how many ways? Well, one way for a squared b, well, that's still going to be 3 factorial on 2 factorial. But now we've got the question, how many ways could we arrange a, b, and c? 3 objects, 3 factorial. So that would be our expansion for a plus b plus c all cubed. Now, it looks like a lot of work, but it's less work than physically expanding the whole thing out. Oh, what the heck, let's do a plus b to the power of 4, because it's just fun. So what could we have? We've got 4 sets of parentheses now. We've only got the pronumerals a and b. We can take 1 out of each. What could we come up with? All right, we could take a out of all of them. So we could have something to the power of 4. I could take a out of 1, b out of the other 3. Or I could take a out of 2, b out of 2. That pretty much covers everything. Now we just ask the question, how many ways could we arrange? Well, the a to the power of 4, so that's just going to be 1. ab cubed. So if I said, how many ways could I arrange a, b, b, b? Well, that's going to be 4 factorial on 3 factorial. A squared, b squared. So a, b, b. 4 factorial on 2 factorial, 2 factorial. And tidy that up, there is our expansion. Now, I don't want you to panic about this, because I'm just extending the idea a little bit. Because you'll notice in the sheets I did write it as extension, so it's extension to extension, if you like. But I just thought it was interesting to look at. So let's try this one. A plus b plus c to the power of 4. So we've got 4 parentheses. Each of them have got a, b, and c in it. All the different things we could come up with. Well, we know we will get a to the 4 plus b to the 4 plus c to the 4. Fair enough. We will get, well, I could take a out of 1 and b out of 3 others. So all those ones where I take 1 letter out of 1 and then the other 3 the same. That will be 4 factorial and 3 factorial. I could take 1 letter out of 2 parentheses, and then the other letters. So I get a, b, c squared, a, b squared, c, a squared, b, c. How many ways of arranging that? 4 factorial on 2 factorial. What else could we have? Oh, yeah, we could have I'll take 2 out of 1, sorry, not 2 out of 1, 1 out of 2, and then another 1 out of the other 2. So they end up both being squared. Now, is that everything? Yes, it is. What an expansion. Outstanding. I don't think you'll ever be asked that, by the way. But okay. So say that last little bit of expanding those perfect was just me going a little bit silly. But 15b, remember it's binomial expansions we're looking at.